So the video actually gave us a kind of a preview of some of the things we're going to talk about now. Most chemical reactions occur in several steps. When we look at the chemical equation, we just see what's present at the beginning and what's present at the end. We don't see what might have been formed and destroyed in the middle. We just see the beginning and the end. When we talk about a reaction mechanism, we're going to look at the individual steps that occur in a chemical reaction. When we talk about an elementary step, we're talking about the exact species that are colliding in the reaction. So let's look at this. Here's hydrogen and iodine monochloride. When these react, first of all, a hydrogen molecule runs into the iodine chloride and forms high and HCl. Then this high molecule runs into another ICl, forming HCl and I2. These are the individual steps. They have to add up to the overall reaction. So if we add these equations together, we see that the high that's created here gets destroyed over there. And so the overall reaction would be this. And that's a really ugly 2. I don't even know what that looked like. There we go. So this is the overall chemical reaction. It doesn't tell us what happens in the middle. The mechanism tells us about the individual steps. So this is an elementary step where a hydrogen molecule is crashing into an ICl molecule. And that's making HI and HCl. But the HI will then go on to crash into another ICl molecule and make HCl and I2. So reaction intermediates are these things like high that get made as part of this reaction mechanism, but then they get destroyed again. So they're formed in one step and consumed in another, and you don't, looking from the outside, you never see them. Does anybody have any questions about that? So the reaction mechanism describes the reaction at the molecular level in a complete and detailed way. It's going to show us the individual collisions that occur. So chemical kinetics, how fast things react and how that is affected by things like temperature and concentration, can help us to figure out the mechanism of a reaction. And one way to do that is to first determine the kinetics of the overall reaction and then work backwards to find a mechanism that's consistent with those kinetics. So we can characterize elementary steps by how many reactant molecules there are. And this is called the molecularity of the step. So if the elementary step just involves one molecule, it's called unimolecular, one molecule. If it involves two of the same molecules, it's bimolecular, or two different molecules, also called bimolecular. You have to have two things run into each other. Unimolecular, just one thing reacts itself, spontaneously falls apart or something like that. You can also have termolecular steps that involve three things colliding together, and you can imagine that that would be a lot more complicated, and it's a lot less common. It's very rare. We can deduce rate laws for elementary steps from their equations. Okay, earlier I said we can only determine the rate law based on an experiment, right? And I said, the coefficients, don't try to do that. Okay, this is the one exception, and this is what makes it kind of dangerous, is because you get to use the coefficients to write rate laws here, and then you want to do it everywhere, right? It only works for elementary steps, where we're talking about the exact collision that has to happen. So for A going to products, it has a molecularity of 1. The rate law is just going to be the rate constant times the concentration of that one reactant. The bimolecular ones are going to be second order reactions. Here we've got 2 of the same reacting, so that's Ka squared. Here we have 2 different ones, and that's Kab. Again, you can only do this in elementary steps. Okay? Don't go back to the earlier questions in this chapter and try to do this. It's not going to work. It doesn't work for just a general chemical equation. You could also deduce rate laws for the individual termolecular steps. Those are more rare. So the molecularity is equal to the overall order. Any questions? So usually one of those steps is a lot slower than the others, and that's called the rate determining step, because it limits the rate, it determines the rate. We can use traffic as an analogy for the reaction. You think about a rate limiting section on the highway where these 3 lanes of traffic have to go down to 1 lane because of construction. This area on the freeway is going to limit how fast traffic can flow. You can go really fast at the beginning and really fast after this, but in the middle where the cars have to funnel down into 1 lane, it's going to be slow. That make sense? So this determines the speed that overall you can go on this highway, because you can't go any faster than the slowest part. So if we look at NO2 reacting with CO to form NO and CO2, the experimentally determined rate law is this, K times NO2 squared. Do you see a 2 as a coefficient up here? No. Would you ever guess that this was the rate law based on that equation? Probably not. You'd make a lot of other guesses as well. We can't write the rate law just from the chemical equation. Could this be a single step reaction? If this was a single step, it would be an elementary step, and then the rate law would match, but it doesn't. So it cannot be a single step reaction. So we could come up with lots of different possible mechanisms. So this is one. The NO2 first has to run into another NO2 to make NO3 and some NO, and then this NO3 runs into the CO and makes NO2 and carbon dioxide. And so if we look at this overall reaction, the NO3 is what's called an intermediate. It gets created and destroyed. And so we would end up with, so one of these that started out is returned, and so we can cross that guy out as well. So if we have this reaction step and this reaction step, the overall process is described by the chemical equation. Does that make sense? If this is the slow step, that's going to limit how fast the rate can be. No, I guess. So let's take my scribbles off here and look at this. If this is an elementary step describing exactly what's going to happen, then we can make a rate law for that step. And we would predict that the rate would equal a rate constant times what's happening here. This is colliding with that. It's going to be dependent on this concentration times that concentration. And since they are the same thing, it would be NO2 squared. And that matches up with the experimentally determined rate law. So that suggests that this might be the correct mechanism because it matches what we saw experimentally. It doesn't prove anything, though. So looking at that mechanism, here we have that first step. That was the slow step. So we're going to an intermediate, a transition state, and this has a high activation energy. This is going to be slow. Once you get to this point, then the next one is easy in comparison, and it will just continue on to the products. So this one is fast, and so it's not going to affect the overall rate of the reaction. Questions? Yeah. So for a mechanism to be valid, not necessarily correct, but valid, the elementary steps need to add up to the overall reaction. And the rate law predicted by that mechanism needs to be consistent with the experimentally observed rate law. So we can validate mechanisms, we cannot prove them to be correct. And actually in science, we really can't prove anything to be correct. We can only say no one's been able to prove it incorrect. And that's the best we can do. So we would need other information before we would necessarily accept that proposed mechanism, because there might be other mechanisms that would also fit the descriptions involved. So let's talk about a mechanism with a fast initial step. So the first step is fast. It produces products quickly. Sorry, I'm having a moment here. The first step will often produce reaction intermediates. And because those are intermediates and we don't know anything about their concentration, they cannot be part of an actual rate law. Like with this one. Well, no, that doesn't work. Never mind. So the first step is fast, and then there's some other step after that that's slow. If this first step is fast, it can establish an equilibrium. An equilibrium is where the rate of the forward reaction is equal to the rate of the reverse reaction. So if you're just looking at concentrations of reactants and products, the concentrations are staying the same. But if you could zoom in and see what the molecules are doing, you would see that there's molecules reacting to form products, and then there's products reacting to form reactants. And there's actually a lot of activity in there, but overall the concentration doesn't change. Okay, here we have an example. H2 plus no, making H2O2 and N2. Here's the observed rate law. The hydrogen concentration times NO squared. Well, you might say, oh, well, there's a 2. I like that. That has nothing to do with it. And this 2 doesn't show up in there. The coefficients in the overall reaction have nothing to do with the rate law. It would be so easy if they did, but they don't. We'll talk about equilibrium constants in a bit, and then we get to use those, but not here. So here's the mechanism. The first step is very fast. 2 NOs, collide to form N2O2. And then after that, we have a slower reactant, slower step, and then the last step is fast. So first we want to show that condition 1 is met, that the elementary steps add up to the overall chemical reaction. So we'll do that just by adding these 3 equations together. So I'm going to look for anything that appears on both sides. So here's N2O2 and there's N2O2. It gets formed and destroyed. It's not going to show up in the overall reaction. That's an intermediate. Do we have any more? N2O. So we've got H2, but H2 is in the reactants both times. Here we've got N2O and N2O. And that looks like it. So we add up what we didn't cross off. We get 2H2 plus 2. No. Going to 2H2O plus N2. How do you get this from that? Well, you don't directly. You can think up a lot of different mechanisms, and then you have to see if they meet the conditions. Do they add up to the overall reaction? Okay, well that's good, but that's not all that we need to have happen. We need the rate law predicted by this mechanism to be equal to this rate law. So if we look at the mechanism, we have 2NO reacting with N2O2. That's that first step. Right? This guy? And that's a fast one. And then here we have a slow step. What's going to limit the reaction rate? The slow step. So it's an elementary step, and so we can look at that elementary equation and predict the rate law. Again, only if it's an elementary step. And so we can say, well, the rate must be equal to the rate constant times, we're looking at the slow one here, H2 to what power? 1, and N2O2 to 1 power. The first power. We can only do this because this is an elementary step. It is describing exactly which 2 molecules are running into each other. The overall chemical reaction doesn't tell us that. Yeah?
Is the elementary step determined by the slow?
So each of the steps in the mechanism is an elementary step.
Right.
Yeah, each of them is. We're only interested in the slow one here because that's what's going to limit the rate.
Oh.
How fast this one happens doesn't really matter because that's not what's slowing everything down. It's this second step that's slowing everything down. Any questions?
So in like another situation, it could be a fast reaction and still be eliminated.
So we could have the first step be slow,
Okay.
and then that would give us, that would be the rate determining step.
Okay.
Yeah.
So the rate determining step is always the slow one.
Yes, the rate determining step is always the slow one. So this is the rate law that we would predict from this slow step, but this cannot be the rate law for that chemical equation because N2O2 is not one of the reactants. So how would you even test that? You know, to find the constant, you need to measure the concentration of N2O2, but it's not one of the reactants. That's not going to be useful, okay? So what we can do is we can express the N2O2 concentration in terms of reactants from the overall reaction. And what we're going to do here, let me make sure I'm not jumping ahead of myself. No, I'm not, okay. This fast first step we can assume is going to set up an equilibrium. So it's going to have a forward reaction and a reverse reaction, and their rates are going to be equal. So the forward reaction, we could write a rate law. The rate would be equal to the rate constant times no squared. Oops, not NO2. No. And the reverse reaction, this is the reactant, and that's the product. So what would the rate law for that step be? This is the reactant. Yeah, K times the concentration of the N2O2. So this reaction going forward, we could draw with a single arrow looking like this. It's an elementary step. We can predict the rate law. The reverse reaction would be the products reforming the original reactants. So N2O2 going to 2NO. We can also predict a rate law for that. There's just one of these, so a rate constant times that concentration. Everybody okay with that? If this is an equilibrium, the forward rate is equal to the reverse rate. So I'm gonna get rid of my little things over here. So I'm going to set these equal to each other. The forward rate and the reverse rate are happening equal. Now, are these constants the same? No. So let's call this the forward rate constant and the reverse rate constant. We are looking for an expression to replace the concentration of N2O2, which we can't know. So here we've set up an equation, and this has the concentration of N2O2 in it. So if we rearrange this equation, I'm going to divide this side by Kr, and I'm going to divide this side by Kr. So these guys cancel out. The concentration of N2O2 is equal to some constant divided by some other constant times the NO concentration squared. So we can substitute that into our original, into this guy. Oh, go up here. So the rate will equal a rate constant times H2 times NO2 NO squared. There's a little bit of algebra involved in that.
What if we put the KR right there in the bottom, and we crossed it out? How do we do that?
What if we, like, multiply by KR or something?
No,
Or-
that one on the top, the one that
Here?
you're on, yeah.
Yeah, so we did cancel these out. So we moved that constant over here, okay, so that we can get just this by itself.
Okay.
So these are rate constants that we don't know and we don't need to know. We're just going to lump those together and this will be the overall rate constant. That bothers some people, and I understand that. It's an equilibrium. These rates are equal to each other, but the rate constants are not the same. And so, could you, in theory, find out what those rate constants are? Yeah, you could. But, do you need to know that this rate constant is actually 2 times 4 times 3? Or is it enough to know that it's 24? We don't need to know parts of it. We just need to know the overall constant. Does that make sense? Kind of? When you don't understand something, I want you to keep asking questions until you understand it. Okay? Any more questions? The good news is, well, let's do the bad news first. The bad news is you will have to do something like this on an exam. The good news is it'll only be one problem and only on this one exam. So if this is just alphabet soup to you, you can do great in the class without getting this. Some of the other things are super, super important. This isn't one of them. But try. Oops. Okay, so this is a sort of question that could end up on an exam. Ozone naturally decomposes by this overall reaction. We've got an experimentally determined rate law. Show that this proposed mechanism is consistent with the observed rate law. So 2 things have to happen. We have to be able to add these 2 equations to get the original equation. And if we think about adding these, we're going to see that elemental oxygen is an intermediate. And so we would end up with 2 ozones and 3 oxygens. So those add up. Then the next thing we have to do is show that the rate law that we would get from this mechanism is going to agree with this one. So here we have a fast reaction and a slow reaction. The slow reaction is going to be the rate limiting step. And we can predict a rate constant here. We can predict a rate law. And what would that be? It'd be this times this, right? Ugh. Elementary step, we can look at it and write a rate law. It's really great. We want to do it all the time, only for an elementary step. So this doesn't work as the actual rate law because it's got elemental oxygen in it, and that's not one of the reactants. So we're going to look at this fast first step and think about equilibrium, right? The forward reaction rate equals the reverse reaction rate. So we've got O3 going to O2 plus O, that's the forward. And in reverse, we would have O2 plus O going to O3. They're both happening at the same time. We can predict rate laws for each of them. I'll call this constant the forward constant. What's this rate law going to be? K times, there's only O3, right? There's only one reactant, so it's going to be related to that concentration. And the reverse reaction, it's going to be a constant times O2 and O. So let's just, review. Where did I get this? This fast step, we can assume is an equilibrium. So we're looking at a forward reaction. So I wrote that with a single arrow. And the reverse reaction, you don't have to write these out, but initially it helps to see where things are coming from. It's the products going to the reactant. So O2 plus O forming O3. O2 plus O forming O3. One's forward, one's reverse. And we can, because it's an elementary step, we can predict rate laws. Because it's an equilibrium, we know that this thing is equal to that thing. So the forward is equal to the reverse. Everybody okay with that? In the rate law from the slow step, the problem child here is the O. O3 is fine, O3 is a reactant, but O is not. And so we're trying to do something to get rid of the O. So that's why we're doing this forward and reverse are equal. This is the O we're trying to get rid of, so I want to solve this equation for O. And then I can plug it in here and make that go away. Oh, yeah. Oh, it's the O. So I'm solving for O. So I'm going to divide by the other stuff that's on that side. That's a weird bracket, but that's okay. These cancel out. Yes?
So, identifying the kind of problem child or the intermediates is how you would solve for the
Yes, I'm going to look at the slow steps rate law and identify what's the intermediate that I need to get rid of. And so I'm going to take this forward rate law equals reverse rate law equation and I'm going to solve it for this guy. Because I want something I can put in here instead of the concentration of oxygen. Great question. Anybody else? So now we could say that the rate is equal to rate constant times O3 times K reverse, really doesn't matter. K reverse, no, it was K forward, never mind. K forward times O3 divided by KR times O2. And then we're going to use a new rate constant that we're going to clump all of these together. So K, the red K is equal to K times KF times KR. And so we're going to come up with the rate is equal to a rate constant times, okay, let's combine some things here. O3 times O3 would be O3 squared divided by O2. This does not look exactly like that. This has O2 to the -1 concentration. That means 1 over O2. So we can just pull this guy out of the denominator. Also have to move everything over because there's not enough space, and give it a -1. Any questions?
So we just combined all those K's together?
Just combined all the K's together. Yeah. So, you can say, well, this rate constant in this actual rate law is equal to these three other things combined. But we don't need to care about what those three things are, because overall, it's always the same number, and it's just the overall number that we care about. So some people find this fun, and some people find it horrendously confusing. So if you find it horrendously confusing, give it your best shot, but don't stress out about it, okay? And if you enjoy it, have fun.
So,
Yes.
so you're pulling in order to get it to the proper reaction, you're pulling basically the O2 out of the bottom and inversing it, so you get that -1, correct?
Yeah, so the O2 was down here in the denominator, which is 1 over O2,
Okay.
which is the same as O2 to the -1. Yeah. Okay, predict the overall reaction and rate law that results from the following two-step mechanism. Which step is going to determine the rate? The first step here, the slow step, right? What would be the rate law based on that slow step? K times the concentration of A squared. Right? We like doing this. We can only do it for elementary steps, but this is an elementary step. So that's going to limit the rate. Does this have, well, let's not go there. So we're supposed to predict the overall reaction. So we're going to do that by adding these together. Any questions about this? Could this be the rate law for this equation? Why not? Well, there's a B in here. What if it's zero order with respect to B? Then would it work? Yeah. We don't have any intermediates in here. We don't have A2. That would be a problem because it doesn't show up as an original reactant or product. So we can't know what it is. But this just has A. You're right, it doesn't have B, but it could be zero order for B. So this is the predicted rate law for this mechanism. The previous problem, we did all of this algebra and stuff, right? And on this one, because the slow step is first, we can just predict the rate law from the slow step. So I'll just let you know on that exam question, look at it carefully, because it might not be the hard one with a fast first step. It could be an easy one with a slow first step.
So
Okay.
if it's a first slow step, then you can predict the rate law?
Yes. If the first step is slow, you can get the rate law from the elementary step. We don't get the rate law from the overall chemical equation because that would predict A squared times B, and the B isn't in there. The overall rate law has to be determined experimentally. If we know the mechanism, we can predict what that is. Usually we don't actually know the mechanism. We're using the rate law stuff to help us identify if the mechanism is possible. Any questions?